This is Porterville College Physics 104A homework problems for Chapter 5, starting with number 13. Two forces act on a mass. Given the mass and the acceleration, here's one force. What's the other force? So we can set it up like this. We start with F equals ma, the sum of the forces. So let's list out these forces. I've done it in stacked vector notation. The sum, or the first force that we're trying to figure out, we need to figure out its x and y components. So I'll just call those f of x and f sub x and f sub y, plus the given force equals mass times acceleration. The x component becomes f sub x plus negative 1.2 newtons equals 3.1 times 0.91, which is this line. The y component becomes f sub y plus negative 2.5 equals the mass, 3.1 kilograms, times the acceleration, negative 0.27. And so that gives this line right here. Solve each of these equations separately. You get the x component is 4.0 newtons, the y component is 1.66 newtons. So the vector, the mystery vector, is 4 I hat plus 1.7 j hat newtons. Number 15 does a derivation that we've done in class, but I'll go through the derivation anyway because it's good to understand where these things come from. We have the object going down the slope, a skier going down a slope, and so here are all the relevant forces. We've got normal force, we have the weight going straight down. There's no friction in this one. I've rotated the coordinate system so x goes down the slope, y goes normal or perpendicular to the slope. So we need to break down weight into its x and y components. And so the x component of weight is w sine theta, the y component is w cosine theta. Once we have the force diagram, we do the sum of the forces equals mass times acceleration for both directions. I'll start here in the x direction. F equals ma. The x component of the force is w sine theta equals ma. And we have acceleration equals g times sine theta. If you do F equals ma in the y direction, you get this. You end up with the result that normal force equals mg cosine theta. Since we're not dealing with friction, which is dependent on normal force, this part isn't going to give us anything useful for this problem. So we're left with acceleration equals g sine theta. Let me flip the page here. Okay, now that we know acceleration equals g sine theta for a frictionless surface, we find the acceleration is 3.986 meters per second squared. Now it becomes a kinematics problem. We have x naught equals 0, v naught equals 0, x equals 1300 meters, and we want to solve for t. So we use this kinematic equation for x. Solving it for t, we get t equals the square root of 2x over a. Plug in the values, including the acceleration that we solved for, and we get 26 seconds. Number 19 involves multiple objects. So we're going to draw force diagrams for each of the two objects and do F equals ma separately for them. Since these are frictionless surfaces, we don't have to, as we found in the previous problem, the normal force isn't going to be relevant. And in fact, I didn't even draw the normal force on those force diagrams. So let's draw the force diagrams. And I should have drawn these normal forces, but I knew they wouldn't matter to the problem. So there's a normal force 2. There, that makes me feel better. And a normal force 1. Okay. So the object on the left with the steeper slope, the relevant force is tension of the rope is pulling it up the slope. mg sine theta and mg cosine theta, those are the x and y components of weight, and you'll notice how I've rotated the coordinate system. And I'll call that angle theta. For the object number 2, I'm calling that angle alpha. It's a separate angle. You notice I've rotated the coordinate system. The rotation of my number 2 coordinate system has nothing to do with my rotation of the number 1 coordinate system. And as I've told you in class, when we're dealing with multiple objects, we can do totally separate coordinate systems. So when we apply F equals ma to the first object, the sum of the forces in the x direction equals 0. So tension minus mg sine theta equals 0. And we can say acceleration is 0 because it says the objects are not sliding. So what we get is tension in the rope equals m1g sine theta. Now, for object 2, we do, as I've set up the coordinate system, mg sine alpha is in the positive direction, minus tension is in the negative direction, equals 0. So tension in the rope equals m2g sine alpha. So from each object I've got an equation or an expression for tension in the rope. Let's set those equal to each other because the tension over here is equal to the tension over here. So when we set those expressions equal to each other, we get m1g sine theta equals m2g sine alpha. The question is asking, how should the masses compare? So a reasonable way to answer that would be to find the ratio of the masses. I've done m1 over m2, and when you solve this equation, that becomes sine alpha over sine theta, and we get 0.394 as the ratio. Or, if you solve it as a ratio of m2 over m1, then you get the reciprocal of 0.394, so 2.5. Number 23, circular motion. Show that the force needed to keep a mass in a circular path of radius r with period t is the expression given in the book. So you follow from F equals ma. Since radial acceleration is v squared over r, then radial force is mv squared over r. If something is moving in a circle, we can say that its speed, or v, is the circumference, the distance it goes around once, divided by the time to go around once. That's the period. So we're going to replace v with 2 pi r over t. Therefore, the radial force becomes this expression. And clean it up, we can divide out 1 power of r, and we show 4 pi squared mr over t squared. Number 29, a hockey puck sliding across the ice. We see the force diagram, so the hockey puck is sliding to the right, therefore friction's going to the left. F equals ma in the x direction gives negative kinetic friction equals ma. Kinetic friction is mu sub k times the normal force. I didn't show it here, but if you do F equals ma in the y direction, you get that normal force minus mg equals 0, so normal force is equal to mg, and we've seen that in class several times. On a horizontal surface, normal force is equal to the weight of the object. So we replace normal force with mg. The m's divide out, and what we get is mu sub k equals negative a over g. Now we have to find out what is that acceleration. So in the blue ink, I've done the kinematics. We have an initial velocity of 14 meters per second, final velocity of 0, displacement of 56 meters, and so we'll use this kinematic equation to find the acceleration. Acceleration is negative v naught squared over 2 delta x, so we get an acceleration of negative 1.75 meters per second squared. Plug that back into the formula for mu sub k that we got up here, negative a over g. and we get mu sub k of 0.18. Number 30. This is a derivation that I've done in class. The end result of the derivation is to find the acceleration, the formula for acceleration that I showed in class, given in this box. But in case you need that derivation again, setting up the forces with gravity, which we're going to break down into its y and x components, friction going opposite direction of motion, and normal force. Here we have F equals ma on the left. I've done it in the x direction. On the right, I've done in the y direction. The y direction, F equals ma, gives us the results that n, the normal force, equals mg cosine theta, which we're going to substitute in here for friction. So after that derivation, we get acceleration equals g times sine theta minus mu sub k cosine theta. From here, it becomes a kinematics problem. We have initial position 0, final position 100 meters, initial velocity 0 meters per second. So we use the kinematic equation. X naught goes to 0, v naught goes to 0, and we're left with x equals 1/2 at squared. Solve for time equals square root of 2x over a. Question 30 asks, how much longer does the run take if the coefficient of kinetic friction is 0.17 instead of 0? So let's solve for those two separate cases. If this is frictionless, mu sub k equals 0, then the acceleration equation just goes to a equals g sine theta. You get an acceleration of 4.6 meters per second squared. Plug it into the time formula, and time equals 6.59 seconds. However, if mu sub k is 0.17, we get an acceleration of 3.1298 meters per second squared. That's going to increase the time because the skier will go at a slower rate. So time is 7.99 seconds. The question asked, how much longer does it take? So the difference between those two times, 1.4 seconds longer due to friction. Number 33. A block is launched up a frictionless ramp. How far up the ramp does it slide? This is reminiscent of problems back in Chapter 2 when looking at something thrown straight up in the air. How high does it go? Well, now we're looking at sending something up a ramp. How high does it go? Except for the fact that we have to solve for acceleration, whereas with a body flying through the air, we just knew the acceleration was 9.8 meters per second squared. We're going to solve this the same way. So first we find acceleration. And I don't want to get bogged down with positive or negative, so I'm just solving for the acceleration, the magnitude of the acceleration, and that's g sine theta because it's frictionless. So 9.8 times sine of 35 degrees, we get an acceleration of 5.62 meters per second squared. Now whether that's positive or negative will depend on how we rotate our coordinate system. I've got x going up the ramp. Acceleration is going to be negative. Since the box is going up the ramp, that's the positive direction. And it's being pulled, acceleration is going to be in the negative direction. If you make x going down the ramp, then acceleration is going to be positive. But its initial velocity is going to be negative. So I made x go up the ramp because that's its initial velocity. But then you have to make acceleration negative. So v naught is 2.2 meters per second. Final velocity, we're looking for the point at which it comes to a stop and then starts to come back down. So final velocity is 0, x naught equals 0. What is x? And this is a good kinematic equation to use. Actually right there. And you solve for delta x and you should get 0.43 meters or 43 centimeters. Number 36. A problem involving three forces that are pulling on an object. We have to make sure we get the angles right. So I've drawn, this is kind of a combination of the illustration and the force diagram. The illustration, we have a 71-degree angle, 28-degree angle, different ropes, so they're going to have different tensions in them. So here are the forces. T1 goes up this way, T2 goes up this way, mg goes straight down. We have to make sure we get the angles right. And angles, we're going to define those off of the positive x-axis. So T1 is no problem. You can see that that's 28 degrees because this is 28 degrees, and that becomes an alternate interior angle. T2, if this is 71 degrees up here, as listed in the book, then this down here is an alternate interior angle, so 71 degrees as well. But we need to give the angle off of the positive x-axis. So you can see that if T2 is 71 degrees shy of 180, because 180 is all the way around to this negative axis, so it's going to be 180 minus 71. So here I have theta 2 equals 109 degrees. That's the proper angle for tension of rope 2. Okay. Now we have the sum of the forces in the x direction, and then we'll do sum of the forces in the y direction. This pack is not accelerating, so sum of the forces in the x direction equals 0. So we write the x components of each force, so that's T1 cosine theta 1 plus T2 cosine theta 2 plus mg cosine 270 degrees, or you can just look at the picture and see that mg is not going to have any horizontal components. Cosine of 270 makes it go away. Equals 0. And what I've done here is solve for T1, because pretty soon we're going to substitute that into another equation and make it go away. You can at this point solve for T2. I solved for T1. Sum of the forces in the y direction. Change all your cosines to sines. So it's T1 sine theta 1 plus T2 sine theta 2 plus mg sine 270 degrees equals 0. And what I've done in the blue is here, from here to here, I've substituted, instead of T1, I'm using the result I've got up here and substituting negative T2 cosine theta 2 over cosine theta 1. Then I solve for T2. So I factor T2 out of these two expressions, get this big expression. So T2 equals the opposite of cosine theta 2 sine theta 1 over cosine theta 1 plus sine theta 2. And I added mg to both sides of the equation, so mg is now on the right-hand side. An intermediate answer, that expression in the brackets with all the cosines and sines, I got 1.1186 equals m times g. And when I solve for T2, I get 230 newtons, and that's rounded to proper significant figures. T1, I go back up to my expression, T1, plug in for T2, and by the way, for T2, don't use the rounded expression of 230 newtons. Use it to a few more significant digits. So I used 227.8 newtons, plugged it into my expression for T1, and got 84 newtons. So those are the tensions of the two ropes. Number 43. Number 43, a child slides down a slope at constant speed. What is the frictional coefficient? Constant speed means zero acceleration. So we have the expression A equals, or the equation A equals G sine theta minus mu sub k cosine theta. For the derivation of that, go back to C problem number 30 on this video. Acceleration equals 0. So when we solve for mu sub k, we get sine theta over cosine theta, or tan theta. So the tan of 12 degrees, and we get 0.21. Number 46. I like this one. A bat crashes into the vertical front of an accelerating subway train. Frictional coefficient between bat and train is 0.86. What's the minimum acceleration of the train that will allow the bat to remain in place? So you look at the force diagram. There's my bat crashed against the subway, and the forces are frictional. Static friction is pointing upward because the bat otherwise would slide down, so static friction is what's keeping it up, so that points upward. Gravity is pointing down. The normal force between the bat and the subway is pointing to the right in the direction that the subway is going. So we will then apply sum of the forces in the x direction and in the y direction equals mass times acceleration. Let's start up here. Sum of the forces in the x direction equals mass times acceleration. So the only force in the x direction, normal force, equals ma. Now we do that equation in the y direction. Sum of the forces in the y direction equals, and we don't want it accelerating the y direction, so equals 0. The forces in the y direction, we have static friction minus mg equals 0. So mg equals static friction, and remember, static friction is less than or equal to mu sub s times the normal force. So now we have mg is less than or equal to mu sub s times, and here's that substitution. Instead of normal force, we'll say ma. The mass of the bat divides out, and we're left with g is less than or equal to mu sub s a, which means acceleration is greater than or equal to g over mu sub s. And here I've flipped left and right. So acceleration greater than or equal to 9.8 meters per second squared divided by 0.86, 11 meters per second squared. So the acceleration needs to be at least 11 meters per second squared for the bat to stay up.